Hello, myself Naveen Kumar Saini. In the course Electromagnetic Field Theory, code KEE 301, lecture number 22, and we are in transmission line unit 5. So, in that, as we have discussed in the previous lecture about basics of the transmission line and the transmission line equations in the voltage and the current form. And two special cases we have covered in the last lecture about the transmission line in the distortionless line, okay, and the lossless line. These two cases we have covered in the last lecture. So today we are going to discuss about the input impedance, SWR, standing wave ratio, and the power. So this content we are going to discuss in this lecture. So in the last lecture we have discussed about what is a transmission line, and we said about the transmission line, it is a distributed architecture. In that in the conductors we have that conductor is defined as the resistance per unit length and the inductance per unit length, and the intermediate medium between the two conductors, that is defined by the component transconductance and the capacitance. Okay, so from that one section we are taking. So suppose we have this transmission line and we cut this transmission line. So this section we are taking from this transmission line, this is the conductor, and in between this is the some kind of substrate is there or the material is there. So we are taking one section and we just want to know what is the input impedance at this point. Okay, so for that we are taking this section as z is equal to z0 or z is equal to 0, and this one is at the z is equal to L. So the section of transmission line which is of L length. So in that, at the load side, this is the load side. So this is the load side in comparison with that. So we are applying the one of the source Vg, through which the current which is flowing, that is the I0, and it is passing through the conductor. So this is the conductor, and this complete section is the transmission line, and the output of this one is the IL. At the load side we have the voltage, that is the VL, and the load impedance, that is load is the ZL. So this is the ZL is a load. So and this transmission line is defined as a two parameters, as we said, if you remember in the last lecture. Two parameters are the gamma and the Z0. Gamma is propagation constant and Z0, this is the characteristic impedance. So why we define this gamma and Z0? As I said and I explained last year, that gamma is nothing but this is R plus J G, okay, and here that is L, this is your L plus C, J omega C. Okay, so these parameters we have defined about the gamma. Okay, in this J omega L, so this is will be your J omega L. So you can change it, J omega L and L plus J omega C. Okay, so this equation we had derived in the last lecture, and how this equation looks like about the gamma and the Z0. So these two parameters are contains the four transmission line parameters. What was that? R, this is a ohm per meter or the resistance per unit length, L Henry per meter or inductance per unit length, G Siemens per meter, and C is the farad per meter. So we have considered the transmission line which is of length L, characterized by the two parameters gamma and Z0, and these are connected to the load ZL. Okay, so we are looking into the line from this side or towards from the generator side. We see that the line with the load as an input impedance Z in. It is our intention in this section to determine the input impedance. So these are the parameters which we want to calculate: standing wave ratio and the power flow. So this is the analogy diagram of above one, where Vg is the source voltage we are applying, Zg, this is the impedance at the input impedance side, I naught is the current, V naught is the voltage across the Z in. Okay. So here we are taking the this Z in is the impedance. Okay, and across this Z in we have the V naught. So this section we are assuming. Okay. So this is the general representation of the diagram which we in the network theory as well. So what we do, we will apply the KVL KCL here, so that we can find some of the input impedance parameter and the SWR and power. So if you remember about in the last lecture, we have discussed about the voltage and the current equations, where voltage equation is VSZ, V naught plus e की power minus gamma z and this much. So the significance of this equation is, at an instant at voltage is Vs, and it shows that this is equal to V naught plus e की power minus gamma z. So what this representing? This representing the wave is propagating in the plus z direction. So this section is for the wave propagating the plus z direction, and this one is the wave propagating in the minus of z direction, due to which the standing waves will be generated. And the next equation, this is for the current equation which we derived, V naught plus upon Z naught e की power minus gamma z minus V naught upon Z naught e की power gamma z. This is also representing the plus z direction and minus z direction. So to find, we are just going to solve these equations. If this is equation number 1, this is equation number 2. So to find V naught plus and V naught minus, so what we will do, we will apply some conditions. Okay, so for that condition we are taking the input side. So what is the input side when the Z is equal to 0? If you see here, at Z is equal to 0, voltage is V naught and the current is I naught. Okay, so when you apply this condition in the above two equations and solve the equations, okay, so just put at Z is equal to 0 in this equation. So what this equation will be, Vs 0, this is nothing but V naught, is equal to, from this one it will be V naught plus, this is the Z is equal to 0, so this term will become 1, okay, plus V naught minus. Similar to that, from this equation we will get the Is at Z is equal to 0, this will become the I naught, is equal to V naught plus upon Z naught minus, this equation will become V naught minus upon Z naught, okay, because Z is equal to 0. So e की power 0 is equal to 1. So now this equation become V naught is equal to this much and I naught is equal to this one. So when we solve these two equations and we want to find the V naught plus and V naught minus, so after solving we will get the V naught plus is equal to half V naught plus Z naught I naught, okay, and here V naught minus is equal to 1 by 2 V naught minus Z naught I naught. I hope this point is clear to all of you. Then now come to the point here in this equation here. So now we will use this equation, this graph. So Vz is that much, Zg I naught Z in. So here what we are taking, we are taking the V naught. So V naught will be what? Here we can see V naught is what? V naught is Z in divided by Zg plus Z in into Vg. Z in upon Z in plus Zg into Vg. Voltage divider rule we are applying here, and I naught is Vg upon Z in plus Zg. So now, so this is the equation number 3, equation number 4. Now we have this equation number 5 as well. Now we will find the equation for the Z is equal to L. Okay, so VL will be equal to V at Z is equal to L, and IL when Z is equal to L. So, the two sections we are talking about. First one as the at this one z is equal to 0 and this one as the z is equal to L. Okay. So, we have discussed about this section at z is equal to 0. Now, we want to discuss about the z is equal to L. So, in this case at this point here was the V naught I naught, here is the VL IL. Okay. In this section, this is the input side and this is the output side. So, VL, this one again we will do the same thing, we will apply here this in this equation. What we are doing, we will put the V naught plus e की power minus gamma L, here is L, V naught minus e की power gamma L, right. In place of Z we are putting the L. So, when we put it and we solve these equations, then V naught plus and V naught minus we can get it in this way, V naught plus and I naught minus. So, V naught plus will be half VL plus Z naught IL e की power gamma L, and here it is the half VL minus Z naught IL e की power minus gamma L. Okay. Now, our main concern is about the input impedance Z in we want. So, the input impedance will be what? The input impedance will be VSZ upon ISZ at any point on the line. So, input impedance we can find here. So, input impedance can be find at Z is equal to 0, Z is equal to L minus 1, Z is equal to L minus 2 and so on, or at any instant of Z. So, we can put the value of Z and at that moment or at that distance we can find the Z in. Fine. So, for that Z in we are taking as VSZ IS Z naught. So, we are taking this as from this section from here. Okay. So, from this one V naught plus and V naught minus we are getting, and V naught and V I naught we are getting here. So, when we put VSZ upon ISZ, so this equation will be Z naught V naught plus V naught minus upon V naught plus minus V naught minus. So, this is the case at the point where we are taking the Z as Z into the consideration, and we will put the at Z is equal to 0. So, this expression we are getting here. So, what we will do now, we will put the value of V naught plus and V naught minus from the general case at L. Okay. So, when we put it here, so in this way we have to use find some of the expression from trigonometry, that e की power gamma L plus e की power minus gamma L by 2 is equal to cos hyperbolic gamma L, and for sin hyperbolic gamma L we can get it e की power gamma L minus e की power minus gamma L by 2, and tan hyperbolic gamma L will be like this. So, how we are getting this? So, for this we are applying, so we can see, so in this equation we are putting the Z naught, V naught plus we can take it here and V naught minus from here. So, V naught plus we can take V naught plus V naught minus. So, if we put it, then it will be half VL minus Z naught plus Z naught I naught IL e की power gamma L plus half VL minus Z naught IL e की power gamma L. Clear? Fine. Similarly, we can find the V naught plus minus V naught minus, that is equal to half, that is VL plus Z naught IL e की power gamma L minus half VL minus Z naught IL upon e की power gamma L. So, we can combine these equations. What we can do? So, just simply when you use this one and you can take IL outside, so IL will be cancelled out, and when we get the VL divided by the IL, this value will be ZL. Okay. So, when we put it here all together, so the expression which we are getting here, it will be this one. ZL Z in that is equal to Z naught e की power ZL plus Z naught tan hyperbolic gamma L upon Z naught plus ZL tan hyperbolic gamma L. So this is the general case for the lossy case or the lossy medium. Okay. So this point is clear. This is very simple. First, what we have done, we have simply calculated the at Z is equal to 0, we have taken these terms and we put it here and we find the value of V naught plus and V naught minus, the first case. Second case, what we have done, we found the at Z is equal to L. So from this one again we found the V naught plus and V naught minus. So V naught plus and V naught minus we have calculated for the Z is equal to 0 and Z is equal to L. Okay. Now next step, the third step, what we have done, we have used this equation Z in is equal to Vs Z upon Is. So in that we have taken at Z is equal to 0, this equation will become this one, Z naught V naught plus V naught minus upon V naught plus V naught minus. Okay, so this equation we have taken at Z is equal to 0. So in the general case, when we want it at the some instant at any point on the transmission line, so in place of V naught plus and V naught minus, we have used these equations. Okay, so V naught plus and V naught minus we have taken from here, and separately you can find the V naught plus V naught minus here and the V naught plus V naught minus from here. So in that you can club the equations, and in this way what you need to do, next step is to take the IL outside from these two equations, this one and this one. So we will get the term VL upon IL, it will be ZL, and we club the equations in that way that we will get this type of expression into it, e की power gamma L plus e की power minus gamma L. Okay, and where we find this, we will put it as the cos hyperbolic gamma L, and when we found this expression e की power gamma L minus e की power minus gamma L divided by 2, then in place of this we will put the sin hyperbolic gamma L. So when we do some calculations or real adjustments, then we will find tan hyperbolic gamma L will be equal to this one. So when we interface, when we get it this expression, in place of that we can put the tan hyperbolic gamma L. So please practice this one, things are very easy. So Z in will be equal to Z naught ZL plus Z naught tan hyperbolic gamma L divided by Z naught plus ZL tan hyperbolic gamma L. So this is the case when we have the length Z is equal to L. So we can find any value of Z in by varying the value of Z. Okay, Z, as we have mentioned the maximum limit of L, we can increase the limit at instant, we can find the value of the Z in. So this Z in will defined by the based on the value of L. Okay, gamma L. Gamma is propagation constant, L is the length of the transmission line. So in this way, this expression and here Z naught is characteristic impedance, ZL, this is a load impedance here. So when we solve this one, then in the lossy case, in the general case, we can find the Z in when the your medium is completely distorted. So there is some of the cases are also here which we can apply, as we have discussed the lossless case, okay, lossy case, distortion case. So all these cases we can consider here. So for the lossless case, we had derived about the this propagation constant gamma, that is equal to J times of beta. Okay, so we have covered about that gamma, that is equal to alpha plus J beta, and in the lossless case, this is a lossless case, alpha is equal to 0. Okay, so gamma was, that is equal to J into beta. So in the previous equation here, what we need to do, simply we will put in place of gamma, we can put the J beta. This is the case for the lossless. So here equation Z in will be equal to Z naught ZL plus J Z naught tan beta L upon Z naught plus J ZL tan beta L. So this is the case of the lossless dielectric. Next is the reflection coefficient or the voltage reflection coefficient at the load. So this expression we have we know this formula that gamma L is equal to V naught minus e की power gamma L upon V naught plus e की power minus gamma L. So we can put this equation V naught minus and V naught plus from the above equations, and the final expression which we will get the gamma L is equal to ZL minus Z naught upon ZL plus Z naught. So when we put all these equations, then this final expression we can get very easily. So voltage reflection coefficient. So this is a definition for that. Voltage reflection at any point on the line is a ratio of reflected voltage wave to that of the incident voltage. Okay. So in this way we can put at any instant where the Z, that is L, from the, this is from the load side, so L minus L dash. So when we put this equation here, then the expression will be gamma L e की power minus 2 gamma L dash. So L dash is nothing from the ZL. Okay. So in this way we can find this maximum value of Vmax and the Vmin, and maximum value of current and the minimum value of the current. So this ratio is nothing but the standing wave ratio, and this expression is, which we are getting, SWR is equal to 1 plus gamma L upon 1 minus gamma L. Okay. So this is the reflection coefficient, this one is the standing wave ratio. Similar to that, the minimum value Z in max we can also find out with the help of this expression, that V max upon I min, that is S is the standing wave ratio into Z naught. Similarly, Z in minimum will be Z naught upon S. Okay, so these are very important expressions for the minimum and maximum value of the Z in. About the power, so this formula we have already discussed about that, the real part of the power, that is the real power or the average power, which are used in the Poynting vector as well. The half real part Vs L and Is asterisk or the Hermitian L. So when we put for the lossless case, so simply we can put the lossless case here. So when we do some of manipulation in this equation, then the final expression which we get in this way. Half real part of this equation is V naught plus square by Z naught 1 plus gamma square plus gamma e की power 2 j beta L and gamma asterisk or conjugate e की power j beta gamma L. Okay. So the power is, average power is given in this way, V naught plus square upon 2 Z naught 1 minus mode of gamma square. For the shorted line, these are special cases here. For the shorted line, ZL is 0 and ZSC, this is input impedance at ZL is equal to 0. So J Z naught 10 beta L and gamma L is equal to minus 1, S is equal to infinite. For the open circuited line, ZL is infinite. So input impedance will be ZOC, open circuit, when the ZL is infinite. So the expression which we are getting minus JZ naught cot beta L. In that gamma L is 1, S is infinite, and this is the expression or the equation which we are getting, relation between the short circuit and the open circuit impedance, that is equal to the square of the characteristic impedance. Meshed line, this is the last point, when ZL is equal to Z naught, in that the Z in will be equal to Z naught. So the characteristic impedance will be equal to the input impedance of the transmission line. So I hope this topic is clear to all of you. This was the last topic of unit 5. So I hope as we have covered a transmission line, this will be very helpful to all. Thank you very much.